Each and every day, thousands of aircraft take off and safely arrive at their destinations. Naturally, pilots always seek to make each flight an enjoyable one and do their best to provide passengers with a comfortable and safe flight. Nevertheless, airplane upsets and resulting loss of control have been a major contributor to accidents in commercial aviation. Airplane upsets can result from a variety of causes, including flying into unexpectedly harsh weather conditions or experiencing system malfunctions. It is therefore essential that pilots receive proper training to address these situations. When we use the word upset throughout this program, we are referring to either an abnormal attitude or an abnormal angle of attack, or a combination of both. For the sake of clarity, we shall define upset as pitch attitude of more than 25 nose up, or more than 10 degrees nose down, or bank angle of more than 45 degrees, or pitch and bank angles within limits, but at a speed that is inappropriate for the current flight profile. An upset may present just one of the above conditions or a combination of them. A pilot must be able to identify an upset as early as possible and subsequently take the proper course of action. Thus, identifying and understanding the causes of an upset is extremely important. The causes of airplane upset are varied, but they may be broadly categorized as environmentally induced, that is, by either turbulence or wind shear, brought about by an aircraft malfunction, or caused by human factors. In this regard, environmental factors are the main causes of airplane upsets. Atmospheric turbulence exists when there are large variations of air current, direction, intensity, or both, over a short distance. Turbulence intensity can be classified as light, moderate, severe, or extreme. Pilots need to have the necessary skills to recognize the types of turbulence that can lead to an upset situation and must possess the ability to avoid these situations. Clear air turbulence cannot always be foreseen, and therefore such an encounter may be without warning. In this situation, turbulence can occur when no clouds are visible. Clear air turbulence is common at high altitudes, where cruising aircraft can suddenly enter turbulence areas caused by jet streams. Jet streams are fast, high-altitude currents which disturb air nearby. In general, areas of turbulence associated with a jet stream are from 100 to 300 miles long, elongated in the direction of the wind, 50 to 100 miles wide, and 2,000 to 5,000 feet deep. These conditions may persist from 30 minutes to 1 day. Another kind of turbulence, called mountain wave turbulence, is caused by mountains disrupting wind flow. Rotor clouds are positive signs of this so-called mountain wave turbulence. A severe turbulence encounter can be characterized by large, abrupt changes in aircraft altitude and attitude, and is commonly associated with mountainous areas, where there are large perpendicular wind components exceeding 50 knots near mountain ridges, or in or near fully developed thunderstorms. This type of turbulence can also cause significant changes in indicated airspeed and may catch pilots by surprise, resulting in loss of control of the aircraft. The term wind shear refers to a sudden change in wind direction or speed that can expose aircraft at low altitudes to a serious hazard. These variations can arise from a wide diversity of meteorological conditions, such as a topographical condition, temperature inversions, sea breeze, frontal systems, strong surface winds, and the most violent form of wind changes, thunderstorms and rain showers. In a wind shear, wind may shift from a tailwind to a headwind or to a downdraft or updraft. The consequences may be an abrupt change in airspeed, lift and altitude, upwards or downwards, according to the wind shear's relative direction. For instance, the following scenario may transpire as an aircraft flies through a downdraft. An airplane encountering a headwind after takeoff appears to have good performance characterized by high indicated airspeed, which may induce the pilot into rotating the airplane to a pitch angle higher than usual. When a thunderstorm core is reached, wind shifts to a downdraft and airspeed decreases, as well as vertical speed. The pilot's natural reaction is to lower the airplane's nose in an attempt to maintain airspeed. Further ahead, wind shifts to a tailwind component, resulting in a dramatic airspeed reduction with the nose already down. Studies of wind shear-related crashes have shown that the accidents were caused by aircraft encountering concentrated, small-scale, jet-like downdraft, known as microbursts, rather than gust fronts. Downdrafts associated with microbursts are typically only a few hundred to 3,000 feet across. When a downdraft reaches the ground, it spreads out horizontally and may form one or more horizontal vortex rings around the downdraft. Wind speeds intensify for about 5 minutes after a microburst initially contacts the ground and typically dissipates within 1 to 20 minutes after ground contact. Aircraft wake turbulence encounters have been a leading cause of aircraft upsets induced by the environment. The phenomenon that creates wake turbulence results from the forces that lift the airplane. High-pressure air from the lower surface of the wings flows around the wingtips to the lower pressure region above the wings. A pair of counter-rotating vortices is thus shed from the wings. The right wing vortex rotates counterclockwise, and the left wing rotates clockwise. The region of rotating air behind the airplane is where wake turbulence occurs. The strength of the turbulence is determined predominantly by the weight, wingspan, and speed of the airplane. Generally, vortices descend at an initial rate of about 300 to 500 feet per minute for about 30 seconds. The descent rate decreases and eventually reaches zero at between 500 and 900 feet below the flight path. Flying at or above the flight path provides the best method for avoidance. Maintaining a vertical separation of at least 1,000 feet when crossing below the preceding aircraft may be considered safe. An encounter with wake turbulence usually results in induced rolling or pitch moments. In more than one instance, pilots have described an encounter to be like hitting a wall. Counter control is usually effective, and induced roll is minimal in cases where the wingspan and ailerons of the encountering airplane exceed beyond the rotation flow field of the vortex. However, it is more difficult for airplanes with short wingspan, relative to the generating airplane, to counter the imposed roll induced by the vortex flow. Avoiding wake turbulence is the key to avoiding many airplane upsets. Pilot and air traffic control procedures and standards are designed to accomplish this goal. Keep it clean is a universal axiom applicable to aerodynamically critical aircraft surfaces. Even thin and rough icing adhering to the aerodynamic surfaces can cause degradation in flying qualities and aircraft performance. Guidance on how to avoid and handle icing conditions can be found in the Embraer video named Operation in Icing Conditions, available to all Embraer operators.